look up. Just for a moment, let your eyes drift into the velvet blackness above. What you are seeing is not just a collection of distant lights, it is a tapestry woven from the very fabric of time and space, a canvas painted with the ghosts of the universe's infancy. Every single point of light, every smudge, every spiral is a galaxy, a city of 100 billion stars, each one a monument to a cosmic struggle that began nearly 14 billion years ago. We live in the Milky Way, a magnificent spiral, but how did this colossal structure, and all the others like it, come to be? How did the smooth, featureless perfection of the early cosmos give way to the breathtaking complexity we see today? This is the story of the universe's greatest architectural feat, a tale of unimaginable forces, of a silent, invisible hand guiding the destiny of everything. It is the story of the first light, the first stars, and the birth of the first galaxies. It is a story that is, in a very real sense, our own origin story. If you are ready to embark on this journey with us, to peer back into the deepest depths of time and witness the cosmic dawn, then take a moment to like this video and subscribe to Cosmo Depth. It is your support that allows us to continue bringing these epic untold stories of the cosmos to light. Now let us begin our descent into the darkness, into the time before time, to the moment when the universe was less than a second old. Our journey begins not with a bang, but with a whisper of energy, a point of infinite density and temperature, a singularity that contained the blueprint for everything that would ever exist. The Big Bang was not an explosion in space, but an expansion of space itself. It is the beginning of time, space, and matter as we know it. But even the Big Bang model, in its original form, left cosmologists with profound, unsettling questions. The universe seemed too perfect, too uniform, and too flat to be explained by simple expansion alone. This is where the concept of inflation enters the narrative, a period of hyper-rapid expansion that lasted for a fleeting moment, yet fundamentally shaped the entire future of the cosmos. Imagine the universe at 10 to the power of negative 35 seconds old. It is a realm governed by quantum mechanics, a place where the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were unified into a single, symmetrical superforce. Then, a phase transition occurred, much like water freezing into ice, causing the universe to undergo a period of exponential growth. In less than a trillionth of a second, the universe expanded by a factor of at least 10 to the power of 26, possibly much more. This is a scale of expansion that defies human intuition. If you were to inflate a marble to the size of the observable universe in that time, you would begin to grasp the sheer magnitude of this event. This inflationary epoch, proposed by Alan Guth and others, elegantly solved the two most vexing problems of the standard Big Bang model: the horizon problem and the flatness problem. The horizon problem asks why the cosmic microwave background, the oldest light in the universe, is so uniform in temperature across the entire sky, even in regions that were causally disconnected at the time the light was emitted. The answer is that, before inflation, these regions were close enough to communicate and reach thermal equilibrium. Inflation then stretched them far beyond each other's horizons, preserving that initial uniformity. The flatness problem addresses the observation that the universe's geometry is incredibly close to flat. Inflation predicts that any initial curvature would have been stretched so flat that it is indistinguishable from perfect flatness today. Much like a tiny wrinkle on a balloon becomes smooth when the balloon is inflated to an enormous size. But the most crucial contribution of inflation to our story is the creation of the seeds of structure. In the quantum realm, nothing is perfectly still. There are always tiny, random fluctuations in energy density. Inflation took these microscopic quantum jitters and stretched them across the vast, newly inflated cosmos, transforming them into macroscopic variations in density. These minute variations, differences of only a few parts per 100,000, are the ripples in the primordial soup, the subtle differences in mass that would one day become the great walls and superclusters of galaxies. Without inflation, the universe would either be a chaotic mess of black holes or a featureless void. Instead, we have a universe that is both remarkably uniform on the largest scales and wonderfully clumpy on smaller scales. The very existence of galaxies, of stars, of us, is a direct consequence of these quantum seeds planted during that fleeting moment of hyperexpansion. As the inflationary period ended, the energy driving the expansion was converted into a hot, dense plasma of elementary particles, quarks, leptons, and their antiparticles. This process is known as reheating. The universe was now a searing hot, opaque soup, a state of matter unlike anything we can experience today. The next phase of our journey takes us through the first 3 minutes of the universe's life, a period of intense nuclear activity known as Big Bang nucleosynthesis, BBN. As the universe continued to expand, it cooled rapidly. Within the first second, the quarks and gluons cooled enough to combine and form the first protons and neutrons. The temperature was still too high for these particles to stick together, but the cosmic clock was ticking. Around the 1 second mark, the temperature dropped to about 10 billion Kelvin, cool enough for the weak nuclear force to stop converting protons into neutrons and vice versa. The ratio of protons to neutrons was effectively frozen at about 7 protons for every 1 neutron. This ratio is critically important, as it determines the final elemental composition of the universe. The next 2 minutes were a race against time. The universe was still cooling, and at about the 3-minute mark, the temperature dropped low enough, around 1 billion Kelvin, for nuclear fusion to begin. Protons and neutrons began to fuse, forming the nuclei of the lightest elements: deuterium, heavy hydrogen, helium-3, helium-4, and trace amounts of lithium-7. This process lasted only a few minutes before the universe expanded and cooled too much for fusion to continue. The result of BBN was a universe composed of approximately 75% hydrogen and 25% helium by mass, with tiny traces of lithium. This elemental ratio is one of the most powerful pieces of evidence supporting the Big Bang theory. When astronomers observe the oldest, most pristine gas clouds in the distant universe, they find exactly this ratio. The universe's elemental stage was set, a cosmic stopwatch that determined the raw materials for all future stars and galaxies. But despite the formation of these atomic nuclei, the universe remained opaque. The temperature was still too high for electrons to bind to the nuclei. The universe was a dense, ionized plasma, a fog of charged particles, free electrons and atomic nuclei, that scattered light like a thick cloud. Photons, the particles of light, could not travel freely. They were constantly bouncing off the free electrons. The universe was a blinding, brilliant white, a state of perpetual, universal daylight. This opaque plasma state persisted for a staggering 380,000 years, This is the next great milestone in our story, an event known as recombination or decoupling. As the universe expanded, the temperature finally dropped to a critical point, about 3000 Kelvin, roughly the temperature of the surface of a cool star. At this temperature, the electrons slowed down enough to be captured by the atomic nuclei, forming the first stable, neutral atoms, predominantly hydrogen and helium. This event was the moment the universe became transparent. With the free electrons now bound to the nuclei, the photons were suddenly free to travel unimpeded. They streamed out in all directions, a flood of light released from the cosmic fog. This ancient light, stretched and cooled by the expansion of the universe over billions of years, is what we detect today as the cosmic microwave background, CMB. It is the oldest light in the universe, a perfect snapshot of the cosmos at 380,000 years old. When we tune our instruments to the CMB, we are looking at the universe's baby picture, a relic of the moment when light and matter parted ways. The CMB is a nearly perfect blackbody spectrum, a uniform bath of microwave radiation that fills all space. Its temperature today is a frigid 2.725 Kelvin, just a few degrees above absolute zero. This incredible uniformity confirms the smoothing effect of inflation. But, as we noted earlier, almost is the key word. The true revolution in cosmology came with the discovery of minute temperature fluctuations in the CMB. The Cosmic Background Explorer, COBE satellite, first detected these ripples in 1992, earning its principal investigators the Nobel Prize. Subsequent missions, the Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck satellite, mapped these fluctuations with exquisite precision. They revealed differences of only a few parts per 100,000, tiny, subtle variations in density and temperature. These minute variations are the direct imprint of those quantum fluctuations stretched by inflation. They represent regions of slightly higher and slightly lower density. The slightly denser regions, the warmer spots in the CMB map, are the gravitational seeds from which all structure in the universe would eventually grow. They are the initial conditions for the birth of galaxies. The CMB is not just a picture of the early universe, it is the blueprint for the entire cosmic web. Here is where the story takes a dramatic turn. A turn guided by an invisible, mysterious force, dark matter. The hydrogen and helium atoms that formed during recombination were simply not enough to account for the structure we see today. The gravitational pull of ordinary matter alone would have been too weak, and the expansion of the universe too fast, for the tiny density fluctuations in the CMB to grow into massive galaxies in the time available. Calculations showed that the universe would have remained largely featureless, a vast, empty expanse of gas, if only ordinary matter were involved. Something else was needed, a dominant gravitational scaffolding to pull matter together. That something is dark matter. Dark matter is a substance that does not emit, absorb, or reflect light. It is entirely invisible, interacting with ordinary matter only through the force of gravity. We cannot see it, but we can see its effects, and the evidence for its existence is overwhelming, coming from multiple independent lines of inquiry. The first compelling evidence came from the rotation curves of galaxies. In the 1970s, astronomer Vera Rubin observed that stars on the outskirts of spiral galaxies orbit just as fast as stars closer to the center. According to Newtonian physics, the orbital speed of stars should decrease with distance from the galactic center, where most of the visible mass is concentrated. the only way to explain the flat rotation curves was to hypothesize an extended, invisible halo of mass surrounding the galaxy, a halo of dark matter. This halo provides the extra gravitational pull needed to keep the outer stars moving at their observed speeds. Further evidence comes from gravitational lensing. Massive objects, like galaxy clusters, warp the fabric of space-time, bending the light from objects behind them. By measuring the distortion of these background galaxies, astronomers can map the distribution of mass in the foreground cluster. These maps consistently show that the gravitational mass of the cluster is far greater than the mass of the visible galaxies and the hot X-ray emitting gas. The majority of the mass is invisible dark matter. The most dramatic evidence comes from the Bullet Cluster, a system of two colliding galaxy clusters. Observations show that the ordinary matter, in the form of hot gas, has been slowed down by the collision, but the dark matter has passed right through, separating the gravitational mass from the visible mass. This is a direct visual proof of dark matter's existence and its non-interacting nature. The most dramatic evidence comes from the Bullet Cluster, a system of two colliding galaxy clusters. Observations show that the ordinary matter, in the form of hot gas, has been slowed down by the collision, but the dark matter has passed right through, separating the gravitational mass from the visible mass. This is a direct, visual proof of dark matter's existence and its non-interacting nature. In the early universe, dark matter was the dominant player in the structure formation game. Because it did not interact with the radiation field like ordinary matter, dark matter could begin clumping together much earlier, long before recombination. While the ordinary matter was held back by the pressure of the radiation field, the dark matter was free to collapse under its own gravity, forming vast, interconnected webs of gravitational potential known as the cosmic web. Imagine the universe as a colossal, three-dimensional spider web. The strands of this web are vast filaments of dark matter. The knots are the locations where galaxy clusters will eventually form, and the voids are the immense, empty spaces between them. The ordinary matter, the hydrogen and helium gas, was gravitationally attracted to these pre-existing dark matter structures. It was like water flowing into the deepest parts of a vast, invisible riverbed. The dark matter provided the initial gravitational wells, the cosmic cradles that allowed the gas to collect, cool, and eventually collapse to form the first stars and galaxies. The dark matter is the invisible architect that laid the foundation for all cosmic structure. With the universe now transparent and the dark matter web in place, we enter the cosmic dark ages. This period spans from 380,000 years after the Big Bang to about 400 million years later. The universe was filled with neutral hydrogen and helium gas, but there were no stars, no galaxies, no light sources other than the fading red-shifted glow of the CMB. It was a time of profound universal darkness, a quiet interlude before the cosmic dawn. The only thing happening was the slow, inexorable pull of gravity, driven by dark matter, gathering the gas into ever denser clumps within the dark matter halos. The first structures to form were not full-blown galaxies like the Milky Way, but much smaller, proto-galactic clumps known as mini-halos. These were small pockets of dark matter, perhaps 1,000,000 times the mass of the Sun, that had managed to pull in enough primordial gas to reach a critical density. Inside these mini halos, the gas began to collapse under its own weight. This gas was pristine, composed only of hydrogen and helium, with no heavy elements, what astronomers call metals. This lack of metals made cooling the gas incredibly difficult. In modern star formation, trace amounts of carbon monoxide and dust act as efficient coolants, allowing gas clouds to shed heat and collapse. In the early universe, the only available coolant was molecular hydrogen, which is far less efficient. Consequently, the gas had to reach extremely high temperatures and densities before it could ignite. This led to the birth of the population 3 stars. These were the universe's first stars, born from the pristine, metal-free gas of the early cosmos. They were colossal, truly gargantuan, perhaps hundreds or even 1,000 times the mass of our Sun, and incredibly hot and luminous. Their sheer size and heat meant they burned through their fuel at a furious rate. Because they were so massive, they lived fast and died young, exploding as spectacular supernovae within just a few million years. The brief, brilliant lives of the population 3 stars were the end of the cosmic dark ages and the beginning of the epoch of reionization. The light from these first stars was so intense, so energetic, that it began to strip the electrons from the surrounding neutral hydrogen atoms, reionizing the gas. This process was a gradual, patchy affair, starting in the densest regions where the first stars and proto-galaxies formed, and slowly spreading outward like an infection of light. The universe was transitioning from a neutral, opaque state back to an ionized, transparent state, but this time, the ionization was driven by the light of stars, not the heat of the Big Bang. The epoch of reionization is one of the most challenging and exciting areas of modern cosmology. It is the final major phase transition of the universe, and it took hundreds of millions of years to complete. The James Webb Space Telescope, JWST, is our primary tool for studying this era. By observing the light from the most distant and therefore oldest galaxies, JWST is effectively peering back through the fog of neutral hydrogen, allowing us to map the progress of reionization and understand the sources of the ionizing radiation. Early JWST results have been revolutionary, revealing a surprising number of bright, mature-looking galaxies much earlier than theoretical models had predicted, suggesting that the process of star and galaxy formation was far more efficient in the early universe than previously thought. The supernovae of the population 3 stars had another, even more profound effect. They forged and dispersed the first heavy elements, everything heavier than hydrogen and helium, which astronomers call metals. These elements, such as carbon, oxygen, and iron, were essential for the formation of the next generation of stars, and eventually for planets and life. The death of the first stars seeded the cosmos with the ingredients for complexity. We are, quite literally, stardust, the universe's way of knowing itself. As the universe aged, the small mini-halos merged and grew, following the filaments of the dark matter web. This process of hierarchical merging is the fundamental mechanism of galaxy formation. Small clumps came together to form larger clumps, which then merged to form the first true galaxies. This is a violent, chaotic, and continuous process. Every galaxy we see today, including our own Milky Way, is the result of billions of years of mergers and accretion. The first true galaxies, often called proto-galaxies, began to form around 400 million years after the Big Bang. These were small, irregular, and highly active, forming stars at a furious rate. They were the building blocks of the modern universe. The process of galaxy formation is not a gentle one. It is a story of cosmic cannibalism. When two galaxies collide, they do not simply pass through each other. The stars are so far apart that direct stellar collisions are rare, but the gas clouds and dark matter halos interact violently. The gravitational forces tear the galaxies apart, triggering bursts of star formation as the gas is compressed, and often leading to the merger of their central supermassive black holes. Our own Milky Way is a prime example of this cosmic cannibalism. It is thought to have undergone numerous minor mergers and at least one major merger in its history. We can see the remnants of these mergers today. Streams of stars in the Milky Way's halo, like the Sagittarius dwarf spheroidal galaxy stream, are the ghostly remains of smaller galaxies that were torn apart and consumed by our own. This process is ongoing. The Large and Small Magellanic Clouds, two dwarf galaxies orbiting the Milky Way, are currently being tidally stripped and will eventually be absorbed. In about 4.5 billion years, the Milky Way will collide with the Andromeda Galaxy, a spectacular event that will result in a new, larger elliptical galaxy that astronomers have playfully dubbed Milkomeda. The final shape of a galaxy, whether it is a spiral, an elliptical, or an irregular, is largely determined by its history of mergers and its environment. Spiral galaxies, like the Milky Way, are typically found in less dense regions and have a history of relatively quiet, steady growth. They are characterized by a rotating disk of stars, gas, and dust, with ongoing star formation. Elliptical galaxies, on the other hand, are often found in the dense cores of galaxy clusters and are thought to be the end product of major mergers. They are smooth, featureless, and contain mostly old, red stars with little to no ongoing star formation. The environment plays a crucial role. Galaxies in dense clusters are often stripped of their gas by the hot plasma in the cluster, effectively starving them and turning them into red, dead ellipticals. The growth of a galaxy is inextricably linked to the growth of its central supermassive black hole. Observations suggest that almost every large galaxy harbors a supermassive black hole at its core, with a mass millions or even billions of times that of the Sun. The masses of these black holes are tightly correlated with the properties of their host galaxies, suggesting a profound co-evolutionary relationship. The black hole and the galaxy grow together, each influencing the other. The most striking evidence for this connection is the M-sigma relation, which shows a tight correlation between the mass of the black hole and the velocity dispersion, a measure of the random motion of stars in the galaxy's bulge. This correlation suggests that the black hole is not just a passive passenger. It actively influences the growth of its host galaxy. The mechanism for this co-evolution is complex, but it involves the black hole's ability to regulate star formation through active galactic nucleus, AGN feedback. As gas falls into the black hole, it forms an accretion disk that heats up and emits vast amounts of energy, often in the form of powerful jets and winds. This energy can be so immense that it pushes the surrounding gas out of the galaxy, effectively shutting down star formation. This self-regulating mechanism prevents galaxies from growing too large and too quickly. providing a natural explanation for the observed limits on galaxy size and mass. The black hole acts as a cosmic thermostat, regulating the galaxy's growth and ensuring that the black hole and the galaxy reach their final masses in lockstep. The study of quasars, the incredibly luminous cores of young galaxies powered by actively feeding supermassive black holes, provides a window into this process in the early universe. Quasars are so bright that they can be seen across billions of light years, outshining their host galaxies. Their existence in the early universe, just a few 100 million years after the Big Bang, poses a significant challenge to cosmologists. How did these black holes grow so massive, so quickly? The answer likely involves the rapid accretion of gas and the merging of smaller black holes, a process that was far more efficient in the dense, gas-rich environment of the early cosmos. As galaxies grow, they begin to cluster together, forming groups, clusters, and superclusters, the largest gravitationally bound structures in the universe. Our own Milky Way is part of the local group, which also includes the Andromeda Galaxy and about 50 smaller dwarf galaxies. The local group, in turn, is a small member of the Virgo supercluster, a vast collection of galaxy clusters. And the Virgo supercluster is just one part of the even larger Laniakea supercluster, a structure so immense that it contains the mass of 100 million billion suns. The name Laniakea, meaning immeasurable heaven in Hawaiian, perfectly captures the scale of this cosmic hierarchy. The distribution of these structures is not random. It follows the intricate pattern of the dark matter web. Galaxies are concentrated in the filaments and knots of this web, leaving vast, nearly empty regions known as voids. The universe, on the largest scales, resembles a sponge or a honeycomb, with galaxies tracing the boundaries of the voids. This large-scale structure is a direct consequence of the initial density fluctuations in the CMB, amplified by the gravitational pull of dark matter over billions of years. The motion of galaxies within these superclusters reveals another cosmic mystery: the Great Attractor. Galaxies are not moving randomly, they are all streaming toward a single, immense, unseen concentration of mass, a gravitational anomaly that lies hundreds of millions of light years away. The Great Attractor is a testament to the power of gravity on the largest scales, a region of space so dense that it is pulling entire superclusters toward it. It is a reminder that the universe is still actively evolving, still being shaped by the forces that began their work in the first moments after the Big Bang. The Great Attractor is now understood to be part of the Shapley supercluster, the largest known concentration of galaxies in our local universe, a region of space so dense that its gravitational influence dominates the flow of galaxies over 1 billion light years. The story of the universe is a continuous narrative, a progression from simplicity to complexity. But it is a story with a twist ending. The universe is still expanding, and that expansion is accelerating, driven by another mysterious component: dark energy. The discovery of the accelerating expansion in 1998, based on observations of distant Type O supernovae, was a monumental shock to the scientific community. These supernovae act as standard candles, allowing astronomers to measure the distance to their host galaxies. By comparing the distance with the redshift, a measure of the expansion of space, scientists expected to find that the expansion was slowing down, due to the gravitational pull of all the matter in the universe. Instead, they found the opposite. The expansion was speeding up. Dark energy is a repulsive force, a property of space itself, that is pushing the galaxies apart. It makes up about 68% of the total energy density of the universe. In the early universe, gravity and dark matter were dominant, allowing structure to form. But as the universe aged and expanded, the density of matter decreased, while the density of dark energy, which is a property of space itself, remained constant, or nearly constant. Today, dark energy is the dominant force, and its accelerating expansion is slowly winning the cosmic tug-of-war against gravity. The nature of dark energy is even more mysterious than dark matter. The simplest explanation is that it is the cosmological constant, a term Einstein originally introduced into his equations of general relativity to keep the universe static, a term he later called his biggest blunder. If dark energy is the cosmological constant, it represents the energy of the vacuum of space. However, theoretical calculations of the vacuum energy predict a value that is 10 to the power of 120 times larger than the observed value, a discrepancy so vast that it is considered the worst prediction in the history of physics. This is the cosmological constant problem. Alternative theories suggest that dark energy is a dynamic, evolving field, dubbed quintessence. This field would change over time, potentially leading to a different fate for the universe. Future large-scale surveys, such as the Dark Energy Survey, DES, and the Euclid mission, are dedicated to precisely measuring the properties of dark energy and determining whether it is a constant or a dynamic field. The universe's fate is now sealed. It will continue to expand at an ever-increasing rate. This will lead to the Big Freeze, where the universe becomes cold, dark, and dilute. In the distant future, all galaxies outside our local group will recede from us at speeds greater than the speed of light, effectively disappearing beyond our cosmic horizon. The light from these galaxies will be stretched to such extreme wavelengths that it will become undetectable. The night sky will become a vast, empty blackness, with only the stars of Milkomeda remaining. The nature of dark matter remains one of the most profound mysteries in science. We know it exists. We know how much of it there is. About 27% of the total mass energy of the universe. And we know its gravitational influence, but we do not know what it is made of. The leading hypothesis is that it consists of a new type of elementary particle, a particle that interacts very weakly with ordinary matter. The primary candidates fall into a few categories. The most popular was the WIMP, weakly interacting massive particle. WIMPs are hypothetical particles that would have been produced in the early universe and would interact via the weak nuclear force and gravity. Massive international experiments buried deep underground to shield them from cosmic rays are constantly searching for the faint, rare interactions of these particles with ordinary matter. Experiments like Xenon-T in Italy and the Lux-Zeppelin LZ experiment in the US use massive tanks of super-pure liquid xenon, hoping to detect the tiny flash of light or ionization produced when a WIMP collides with a xenon nucleus. So far, the results have been null, forcing scientists to rule out large swathes of the WIMP parameter space. Another leading candidate is the axion, a much lighter particle proposed to solve a different problem in particle physics. Axions would be much harder to detect, But experiments like the Axion Dark Matter Experiment, ADMX, are using strong magnetic fields and microwave cavities to try and convert axions into detectable photons. The search for dark matter is a multi-pronged effort involving particle accelerators like the Large Hadron Collider, LHC, which attempts to create dark matter particles in high-energy collisions, and space-based observatories like the Fermi Gamma Ray Space Telescope, which looks for the gamma ray signature that would be produced if dark matter particles were to annihilate in dense regions of the galaxy. The discovery of the dark matter particle would be one of the greatest scientific breakthroughs of the century, completing our picture of the cosmic inventory and fundamentally changing our understanding of particle physics. Yet, for now, we live in a golden age, a time when the light from billions of galaxies is still reaching us, allowing us to piece together this incredible story. The journey from the quantum fluctuations of inflation to the grand spirals of the Milky Way is a testament to the elegance and power of the laws of physics. It is a story that continues to unfold, with every new telescope and every new discovery adding another layer of detail to this epic tale of gravity and dark matter. We are the conscious product of this cosmic evolution, made of the very elements forged in the hearts of the first stars. The iron in our blood, the calcium in our bones, the carbon that forms the backbone of life. All of it was synthesized in the fiery deaths of those ancient, massive population 3 stars. The quest to understand the universe's origins is the quest to understand our place within it, and it is a journey that will continue for as long as we look up and wonder. To truly appreciate the elegance of inflation, we must delve deeper into the theoretical mechanism that drove it, the inflaton field. This is a hypothetical scalar field, similar to the Higgs field, that is thought to have permeated all of space in the earliest moments of the universe. The energy stored in this field, not the matter or radiation, was the dominant component of the universe's energy density. Imagine a ball sitting on a very flat plateau with a steep hill on one side. The ball represents the inflaton field. When the universe was 10 to the power of negative 35 seconds old, the inflaton field was rolling very slowly down this plateau. This slow roll is the key. The potential energy of the field remained nearly constant, and according to general relativity, a constant energy density acts like a negative pressure, which is the driving force behind the exponential expansion. The universe was not expanding into anything. Space itself was being created at an accelerating rate. The quantum fluctuations we discussed earlier are actually tiny ripples in this inflaton field. As the field slowly rolled, these quantum jitters were stretched and amplified, becoming the classical density perturbations we see in the CMB. This is a profound connection. The largest structures in the universe, the superclusters and voids, have their origin in the smallest, most ephemeral quantum effects. The universe is a giant quantum experiment, and we are the result. The slow roll phase eventually ended when the inflaton field reached the bottom of its potential well, like the ball finally rolling down the steep hill. The field then oscillated violently, and its energy was converted into the hot, dense plasma of particles that marked the beginning of the standard Big Bang model, the process of reheating. The entire inflationary epoch lasted for a tiny fraction of a second, but it set the stage for everything that followed. The fact that the CMB measurements align so perfectly with the predictions of the simplest inflationary models is one of the most stunning triumphs of modern cosmology. The cosmic microwave background is not just a uniform glow, it is a treasure trove of cosmological information. The data collected by the Planck satellite is so precise that it has allowed cosmologists to determine the fundamental parameters of the universe with unprecedented accuracy. When we analyze the pattern of hot and cold spots in the CMB, we are essentially performing a Fourier analysis on the sky, breaking down the complex pattern into a series of simple waves. The resulting graph, known as the power spectrum, is the fingerprint of the early universe. The peaks and troughs in this spectrum correspond to the sound waves, oscillations in the plasma, that were propagating through the universe just before recombination. The position and height of these peaks tell us everything. The first peak, the largest, tells us that the universe is geometrically flat, confirming the prediction of inflation. The second peak tells us the density of ordinary matter, baryons, and the third peak tells us the density of dark matter. The Planck data has given us the definitive cosmic inventory: 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. We are, in essence, a tiny, almost insignificant fraction of the universe's total mass-energy budget. The analysis of the CMB also provides a crucial test for the nature of the primordial fluctuations. The data shows that these fluctuations are adiabatic, meaning that the ratio of photons to matter is constant everywhere, and Gaussian, meaning that the fluctuations follow a simple bell curve distribution. This is exactly what the simplest models of inflation predict. The CMB is the ultimate cosmic ruler, allowing us to measure the size of the universe, its age, and its composition with a precision that would have been unimaginable just a few decades ago. The epoch of Rayonization, the period when the universe transitioned from neutral to ionized, was a critical turning point in the story of galaxy formation. It was a cosmic battle for transparency, and the stakes were high. The primary combatants were the neutral hydrogen atoms and the ionizing photons emitted by the first stars and quasars. Neutral hydrogen is a powerful absorber of ultraviolet light, specifically photons with energies greater than 13.6 electron volts, which is the energy required to strip the electron from the hydrogen atom. The universe was opaque to this light, much like a thick fog. The first sources of light, the massive population 3 stars and the early quasars, began to carve out bubbles of ionized hydrogen in the neutral medium. These bubbles started small, around the first galaxies, and grew larger as more and more sources of ionizing radiation appeared. The process was highly inhomogeneous, with the universe resembling Swiss cheese, where the holes were the ionized bubbles and the cheese was the neutral hydrogen. The key question for cosmologists is, what were the dominant sources of these ionizing photons? Was it the massive short-lived population 3 stars? Was it the slightly less massive, longer-lived population 2 stars that formed in the first true galaxies? Or was it the powerful, non-thermal radiation from the early quasars? Current evidence, particularly from the James Webb Space Telescope, suggests that the first galaxies were surprisingly efficient at producing and releasing these ionizing photons. The sheer number of bright galaxies observed at very high redshifts meaning very early times, indicates that star formation was rampant. These galaxies, though small, were veritable star factories, and their combined light was enough to eventually win the battle, fully ionizing the universe by about 1 billion years after the Big Bang. The universe was finally, truly transparent, allowing light to travel freely across the vast cosmic distances, and allowing us to see the galaxies that formed in that era. The story of galaxy formation is not just about gravity pulling things together, it is also about feedback, the processes that push things apart and regulate growth. Feedback is the universe's way of self-regulating, preventing runaway star formation and ensuring the diversity of galaxies we see today. There are two primary forms of feedback: stellar feedback and AGN feedback. Stellar feedback comes from the stars themselves. The most massive stars end their lives in spectacular supernova explosions. These explosions inject vast amounts of energy and heavy elements into the surrounding gas, heating it up and driving powerful winds that can blow the gas out of the galaxy. This process is particularly effective in small, low-mass galaxies, where the gravitational pull is weaker. Stellar feedback is thought to be the reason why there are far fewer small, faint galaxies than the dark matter model predicts. The gas was simply blown away before it could form stars. AGN feedback, as we discussed, comes from the central supermassive black hole. This is the more powerful and dramatic form of feedback, capable of regulating star formation in the largest galaxies. The energy released by the black hole can take two forms: the quasar mode, or bright mode, and the radio mode, or dim mode. In the quasar mode, the black hole is actively accreting large amounts of cold gas, leading to the immense luminosity of a quasar. The radiation pressure and powerful winds from the accretion disk can clear the gas from the host galaxy, quenching star formation and transforming the galaxy from a blue star-forming spiral into a red, quiescent elliptical. This is the mechanism that links the black hole's growth to the galaxy's growth, ensuring the M-sigma relation holds. In the radio mode, the black hole is accreting gas more slowly, but it launches powerful, relativistic jets of plasma that can extend far beyond the galaxy. These jets heat the surrounding hot gas in the galaxy cluster, preventing it from cooling and flowing onto the galaxy to form new stars. This maintenance mode feedback is crucial for keeping massive elliptical galaxies red and dead over billions of years. The interplay between gravity, dark matter, and these two forms of feedback is what makes galaxy formation a complex, non-linear problem. Cosmologists use sophisticated hydrodynamical simulations like Illustri's TNG to model these processes, attempting to reproduce the observed properties of the galaxy population. These simulations are a testament to our growing understanding of the cosmic forces at play, showing how the simple initial conditions of the CMB can evolve into the rich, complex universe we inhabit. Our own galactic home, the Milky Way, is not immune to the forces of cosmic cannibalism. The most dramatic event in our future is the inevitable collision with our nearest large neighbor, the Andromeda Galaxy, M31. This is not a distant theoretical event. It is a certainty, a gravitational destiny that will play out in about 4.5 billion years. Andromeda is currently approaching the Milky Way at a speed of about 110 kilometers per second. The two galaxies are already gravitationally bound, and the dark matter halos of both are likely already beginning to interact. When the two galactic disks first pass through each other, the gravitational forces will be immense. The stars within each galaxy are so far apart that direct collisions will be rare, but the gas clouds will smash into each other, triggering a massive burst of star formation. The night sky of Earth, assuming it still exists, will be a spectacular, fiery spectacle. The two galaxies will pass through each other, swing back due to their mutual gravitational attraction, and eventually merge completely to form a single, larger, elliptical galaxy. This new galaxy, Milkomeda, or sometimes Milkdromeda, will be a massive quiescent elliptical, a red and dead giant, the final product of a long history of hierarchical merging. The study of this future collision is not just a cosmic curiosity, it is a way to understand the dynamics of galaxy mergers throughout the universe. Astronomers use computer simulations to model the collision, tracking the paths of billions of stars and dark matter particles. These simulations show how the spiral structure is destroyed, how the gas is consumed in a final burst of star formation, and how the two central supermassive black holes spiral inward and eventually merge, releasing a massive burst of gravitational waves. The Milky Way Andromeda collision is a microcosm of the entire story of galaxy formation, a violent, transformative event driven by the relentless, all-encompassing force of gravity, made possible by the vast invisible mass of dark matter. It is the final, grand act of cosmic construction in our local corner of the universe. The search for the dark matter particle is one of the most intense and technologically challenging endeavors in modern physics. It is a war fought deep underground, in the silence and isolation of abandoned mines, far from the noise of the surface world. The reason for going underground is simple: to shield the detectors from cosmic rays, high-energy particles from space that would mimic the signal of a dark matter particle. The sheer rock overburden acts as a massive filter, allowing only the most weakly interacting particles, like neutrinos and hopefully dark matter, to reach the detectors. The detectors themselves are marvels of engineering. The Xenon T experiment, for example, uses a ton of liquid xenon as its target. Xenon is a noble gas that is incredibly dense and can be purified to an extraordinary degree. The detector is designed to look for two simultaneous signals: a tiny flash of light, scintillation, and a cloud of electrons, ionization, produced when a dark matter particle, a WIMP, collides with a xenon nucleus. The ratio of these two signals is the key to distinguishing a dark matter event from background noise. The null results from these cutting-edge experiments have not been a failure. They have been a success of exclusion. They have systematically ruled out the simplest and most favored WIMP models, forcing physicists to consider more exotic and challenging possibilities. This has led to a renewed focus on the lighter dark matter candidates, such as the axion, and even more speculative ideas like sterile neutrinos or primordial black holes. The search for dark matter is a multi-pronged effort involving particle accelerators like the Large Hadron Collider, LHC, which attempts to create dark matter particles in high-energy collisions, and space-based observatories like the Fermi Gamma Ray Space Telescope, which looks for the gamma ray signature that would be produced if dark matter particles were to annihilate in dense regions of the galaxy. The discovery of the dark matter particle would be one of the greatest scientific breakthroughs of the century, completing our picture of the cosmic inventory and fundamentally changing our understanding of particle physics. The story of the universe is a continuous narrative, a progression from simplicity to complexity. But it is a story with a twist ending. The universe is still expanding, and that expansion is accelerating, driven by another mysterious component: dark energy. The discovery of the accelerating expansion in 1998, based on observations of distant Type Ia supernovae, was a monumental shock to the scientific community. These supernovae act as standard candles, allowing astronomers to measure the distance to their host galaxies. By comparing the distance with the redshift, a measure of the expansion of space, scientists expected to find that the expansion was slowing down due to the gravitational pull of all the matter in the universe. Instead, they found the opposite. The expansion was speeding up. Dark energy is a repulsive force, a property of space itself, that is pushing the galaxies apart. It makes up about 68% of the total energy density of the universe. In the early universe, gravity and dark matter were dominant, allowing structure to form. But as the universe aged and expanded, the density of matter decreased, while the density of dark energy, which is a property of space itself, remained constant, or nearly constant. Today, dark energy is the dominant force, and its accelerating expansion is slowly winning the cosmic tug-of-war against gravity. The nature of dark energy is even more mysterious than dark matter. The simplest explanation is that it is the cosmological constant, a term Einstein originally introduced into his equations of general relativity to keep the universe static, a term he later called his biggest blunder. If dark energy is the cosmological constant, it represents the energy of the vacuum of space. However, theoretical calculations of the vacuum energy predict a value that is 10 to the power of 120 times larger than the observed value, a discrepancy so vast that it is considered the worst prediction in the history of physics. This is the cosmological constant problem. Alternative theories suggest that dark energy is a dynamic, evolving field, dubbed quintessence. This field would change over time, potentially leading to a different fate for the universe. Future large-scale surveys, such as the Dark Energy Survey, DES, and the Euclid mission, are dedicated to precisely measuring the properties of dark energy and determining whether it is a constant or a dynamic field. The universe's fate is now sealed. It will continue to expand at an ever-increasing rate. This will lead to the Big Freeze, where the universe becomes cold, dark, and dilute. In the distant future, all galaxies outside our local group will recede from us at speeds greater than the speed of light, effectively disappearing beyond our cosmic horizon. The light from these galaxies will be stretched to such extreme wavelengths that it will become undetectable. The night sky will become a vast, empty blackness, with only the stars of Milkomeda remaining. It is easy to get lost in the abstract numbers and forces, but this story is also a human one, a tale of brilliant minds wrestling with the universe's greatest secrets. The birth of our understanding of galaxies is inextricably linked to the work of pioneers who dared to look beyond the familiar. Consider Edwin Hubble. In the 1920s, the prevailing view was that the Milky Way was the entire universe. Hubble, using the powerful 100-inch telescope at Mount Wilson, observed faint fuzzy nebulae and identified a special type of variable star. the Cepheid variable within them. By measuring the period of these stars, he could determine their true luminosity and therefore their distance. His calculations proved, unequivocally, that the Andromeda Nebula was not a cloud of gas within our galaxy, but a colossal, independent island universe millions of light years away. This single discovery expanded the known universe by an unimaginable factor, fundamentally changing our place in the cosmos. Then there is Vera Rubin. In the 1970s, she and her colleague Kent Ford were meticulously measuring the rotation curves of spiral galaxies. Their work consistently showed the discrepancy. The outer stars were moving too fast. While others dismissed the data, Rubin insisted that the observations were correct, leading her to the inescapable conclusion that there must be a vast, unseen mass, dark matter, holding the galaxies together. Her persistence in the face of skepticism is a testament to the scientific method, and her work laid the foundation for our modern understanding of the universe's composition. And finally, the teams of Saul Perlmutter, Brian Schmidt, and Adam Rees, who, in the late 1990s, set out to measure the deceleration of the universe using Type Ia supernovae. Their shocking discovery that the universe was, in fact, accelerating earned them the Nobel Prize and introduced the world to the concept of dark energy. Their work was a perfect example of a scientific experiment yielding a result so unexpected, so profound, that it forced a complete rewrite of the cosmic narrative. These are the human heroes of our story, the individuals who, through sheer intellect and dedication, lifted the veil on the early universe and the birth of galaxies. Their legacy is the knowledge we now possess, a knowledge that allows us to tell this epic tale. The theory of inflation, so successful in explaining the CMB, leads us down a speculative yet fascinating path, the multiverse hypothesis. If inflation is a process that can start, it can also stop, and if it can stop in one region, it can continue in others. This leads to the concept of eternal inflation, where our universe is just one bubble in an infinitely vast, self-reproducing fractal of universes. This idea is often invoked to address the fine-tuning problem. Our universe appears to be exquisitely fine-tuned for the existence of life. For example, if the strength of the strong nuclear force was slightly different, carbon would not form. If the initial density fluctuations in the CMB were slightly larger, the universe would have collapsed into black holes before stars could form. If they were slightly smaller, no structure would have formed at all. The fundamental constants of nature seem to be set to a razor's edge. The multiverse offers a statistical explanation. If there are an infinite number of universes, each with different physical constants, then it is not surprising that we find ourselves in one of the very few that can support life. It is a form of the anthropic principle. We can only observe the universe that allows observers to exist. While highly speculative and currently untestable, the multiverse hypothesis is a direct, logical consequence of the most successful model of the early universe. It suggests that the birth of galaxies in our universe is not a unique event, but one instance in an infinite, ongoing cosmic drama. It adds a layer of profound, almost philosophical depth to our story, reminding us that the boundaries of our knowledge are constantly being pushed. We have focused on gravity and dark matter, but another, often overlooked force played a subtle yet crucial role in the formation and evolution of galaxies: cosmic magnetic fields. Magnetic fields permeate the universe, from the smallest planets to the largest galaxy clusters. But where did they come from? The Big Bang itself could not have produced the fields we see today. They must have been generated in the early universe, a process known as magnetogenesis. One theory suggests that the first seed magnetic fields were generated during the epoch of ionization, as the first stars and quasars ionized the surrounding gas. Another possibility is that they were generated during the inflationary epoch itself, though this is highly speculative. Regardless of their origin, these seed fields were then amplified by the turbulent motion of gas in the forming galaxies, a process known as the dynamo effect. This is similar to how the Earth's magnetic field is generated by the motion of molten iron in its core. The magnetic fields in spiral galaxies, including the Milky Way, are strong enough to influence the flow of gas, the rate of star formation, and the propagation of cosmic rays. The magnetic field acts as a kind of cosmic pressure, helping to support gas clouds against gravitational collapse in some regions, and channeling the flow of gas along the dark matter filaments in others. It is a subtle, secondary character in our tale, but one that is essential for the full picture of galaxy formation. The study of these fields, often through the observation of synchrotron radiation and the Faraday effect, is a rapidly growing field, adding another layer of complexity to the story of how the universe built its grand structures. Our story began with the birth of galaxies, but let us focus on the process of decline. The universe is currently in a state of slow, irreversible decline in its ability to form new stars. The peak of star formation, often called the cosmic noon, occurred about 10 billion years ago, when the universe was only about 3.8 billion years old. Since then, the rate of star formation has been steadily dropping. The primary reason is the exhaustion of the cold gas supply. Galaxies are the universe's stellar nurseries, and they require cold, dense gas to collapse and form new stars. This gas is being consumed in three ways: star formation, the gas is converted into stars, which eventually lock the material away in stellar remnants. Feedback, the powerful winds and jets from supernovae and AGN expel the gas from the galaxy, heating it up and preventing it from cooling back down. Stripping, in dense galaxy clusters, the hot intergalactic gas can strip the cold gas from the galaxies as they move through the cluster, a process known as ram pressure stripping. As the universe ages, the remaining gas is increasingly hot and diffuse, making it difficult to cool and collapse. The star formation that does occur is increasingly confined to the central regions of spiral galaxies, where the gas is still dense enough. The elliptical galaxies, which have already consumed or expelled most of their gas, are essentially red and dead, their stars slowly fading. The end of the stelliferous era is not a sudden catastrophe, but a slow, gradual decline. A long, quiet sunset that will last for trillions of years. The birth of galaxies was a moment of vibrant, chaotic creation. Their long decline is a testament to the laws of thermodynamics, a slow march toward the cold, dark, and empty future dictated by dark energy. We have spoken of the co-evolution of galaxies and their central supermassive black holes, and the eventual merger of the Milky Way and Andromeda's black holes. But the most direct evidence of these colossal mergers comes not from light, but from the very fabric of space-time itself, gravitational waves. the detection of gravitational waves by the Laser Interferometer, Gravitational Wave Observatory, LIGO, in 2015, a century after Einstein predicted them, opened a new window onto the universe. These ripples in space-time are generated by the most violent events in the cosmos, such as the collision of two black holes or two neutron stars. The black holes detected by LIGO and its partner, Virgo, are typically stellar mass black holes, the remnants of massive stars. However, the technology is rapidly advancing, and future detectors, such as the space-based Laser Interferometer Space Antenna, LISA, will be sensitive to the gravitational waves emitted by the merger of supermassive black holes, the very black holes at the centers of galaxies. LISA will be a time machine, allowing us to listen to the echoes of the early universe, to the sound of the first massive black holes merging as their host galaxies collided. This will provide a direct, independent test of the hierarchical model of galaxy formation, allowing us to trace the growth of these cosmic behemoths from the first quasars to the present day. The universe is not just a visual spectacle, it is a symphony of space-time, and we are just beginning to hear the music of creation. Throughout this narrative, we have spoken of distances in the billions of light years and times in the billions of years. But how do we know these numbers are correct? The answer lies in the cosmic distance ladder, a series of overlapping techniques that allow astronomers to measure distances across the vast expanse of the universe. The first rung of the ladder is parallax, the apparent shift in a star's position as the Earth orbits the Sun. This provides accurate distances for nearby stars. The next rung involves standard candles, objects whose intrinsic luminosity is known. The Cepheid variables which Edwin Hubble used are one such candle. Their period of pulsation is directly related to their brightness. For the most distant galaxies, the final rung of the ladder is the Type Ia supernova. These are the spectacular explosions of white dwarf stars that have reached a critical mass. Because they all explode at nearly the same mass, they all have a remarkably uniform peak luminosity, making them excellent standard candles for measuring the expansion of the universe and, crucially, for discovering dark energy. The entire structure of modern cosmology rests on the precision and accuracy of this distance ladder. Every rung has been meticulously calibrated and cross-checked, allowing us to map the cosmic web, measure the rate of expansion, and ultimately tell the story of the birth of galaxies with confidence. It is a testament to the power of observation and the ingenuity of human science. Finally, let us return to the beginning, to the simple act of looking up. The story of the early universe and the birth of galaxies is more than just a scientific narrative. It is a profound philosophical statement. We have learned that the universe is not static, but a dynamic, evolving entity. We have learned that we are not at the center of creation, but a tiny, fleeting part of a vast, ongoing process. We have learned that the matter that makes up our bodies is the same matter that was forged in the hearts of the first stars and scattered across the cosmos in their explosive deaths. The universe is a place of both immense violence, supernovae, black hole mergers, galactic collisions, and incredible order. The precise tuning of the fundamental constants, the elegant simplicity of the laws of physics. It is a tale of gravity and dark matter, of light and shadow, of birth and inevitable end. Our ability to comprehend this story, to trace our lineage back to the quantum jitters of inflation, is perhaps the most remarkable part of the entire narrative. We are the universe made conscious, the mechanism by which the cosmos can reflect upon itself. The quest to understand the universe's origins is the quest to understand our place within it, and it is a journey that will continue for as long as we look up and wonder. Let us return to the cosmic web, the vast, intricate structure that dark matter built. This structure is not merely a metaphor, it is a physical reality mapped out by the distribution of billions of galaxies. The web is characterized by three main components: voids, filaments, and nodes. The voids are the largest structures in the universe, vast spherical regions that can span hundreds of millions of light years. They are nearly empty, containing very few galaxies, and those that do exist are typically small, faint, dwarf galaxies. The average density of matter in a void is about 1/10 the average density of the universe. These voids are the regions that started with a slightly lower density of matter in the CMB, and the relentless pull of gravity from the surrounding denser regions has been slowly draining them of their contents over cosmic time. The filaments are the long, thread-like structures that surround the voids. They are the highways of the universe, where galaxies are concentrated and where gas flows from the voids toward the denser regions. These filaments are the most common structures in the universe, and they trace the underlying dark matter skeleton. Our own local group resides near a filament that connects us to the Virgo cluster. The nodes are the intersections of the filaments, the densest regions in the cosmic web. These are the locations of massive galaxy clusters and superclusters containing thousands of galaxies and vast reservoirs of hot, X-ray emitting gas. The nodes are the gravitational powerhouses of the universe, the places where the most violent and transformative events, major galaxy mergers, the most powerful AGN feedback, take place. The study of the cosmic web, through large-scale galaxy surveys like the Sloan Digital Sky Survey, SDSS, and the upcoming Dark Energy Spectroscopic Instrument, DESI, allows us to test the predictions of the cold dark matter model with incredible precision. The statistical properties of the web, the size of the voids, the length of the filaments, the spacing of the nodes, are all direct consequences of the initial quantum fluctuations, amplified by dark matter's gravity. The web is the ultimate proof that the universe is a structure built from the bottom up, a testament to the power of a simple initial condition evolving under the force of gravity. The existence of supermassive black holes in the early universe, powering the bright quasars, presents a significant puzzle. How did they form so quickly? The standard model of black hole formation involves the collapse of a massive star, which results in a stellar mass black hole, typically a few tens of solar masses. To grow to 1 billion solar masses in just a few 100 million years requires an incredibly efficient growth mechanism. This has led to the hypothesis of seed black holes, which must have been much more massive than the remnants of normal stars. There are two main theories for the origin of these massive seeds: direct collapse black holes, DCBHs. In the early universe, under certain conditions, specifically a pristine, metal-free gas cloud that is prevented from cooling and fragmenting by a strong ultraviolet background, a colossal cloud of gas could collapse directly into a black hole of 10 to the power of 4 to 10 to the power of 5 solar masses. These massive seeds would then have a head start in the race to become supermassive black holes, runaway stellar collisions. In the dense cores of the first star clusters, massive stars could collide and merge repeatedly, forming a single supermassive star that would then collapse to form a black hole of a few hundred to a few thousand solar masses. The JWST is now actively searching for the observational signatures of these massive seeds, looking for the telltale signs of DCBHS in the most distant galaxies. The discovery of these seeds would be a monumental achievement, completing the story of the co-evolution of black holes and galaxies by revealing the very first steps of the black hole's journey. The birth of galaxies is inextricably linked to the birth of these cosmic behemoths, and the story of one cannot be told without the other. We spoke of the end of the stelliferous era, but let us focus on the process of decline. The universe is currently in a state of slow, irreversible decline in its ability to form new stars. The peak of star formation, often called the cosmic noon, occurred about 10 billion years ago, when the universe was only about 3.8 billion years old. Since then, the rate of star formation has been steadily dropping. The primary reason is the exhaustion of the cold gas supply. Galaxies are the universe's stellar nurseries, and they require cold, dense gas to collapse and form new stars. This gas is being consumed in 3 ways: star formation, the gas is converted into stars, which eventually lock the material away in stellar remnants; feedback, the powerful winds and jets from supernovae and AGN expel the gas from the galaxy, heating it up and preventing it from cooling back down; stripping, in dense galaxy clusters, the hot intergalactic gas can strip the cold gas from the galaxies as they move through the cluster, a process known as ram pressure stripping. As the universe ages, the remaining gas is increasingly hot and diffuse, making it difficult to cool and collapse. The star formation that does occur is increasingly confined to the central regions of spiral galaxies, where the gas is still dense enough. The elliptical galaxies, which have already consumed or expelled most of their gas, are essentially red and dead, their stars slowly fading. The end of the stelliferous era is not a sudden catastrophe, but a slow, gradual decline, a long, quiet sunset that will last for trillions of years. The birth of galaxies was a moment of vibrant, chaotic creation. Their long decline is a testament to the laws of thermodynamics, a slow march toward the cold, dark, and empty future dictated by dark energy. The mystery of dark energy is the final, and perhaps most profound, challenge to our understanding of the cosmos. To unravel its nature, cosmologists are undertaking massive, ambitious projects to map the expansion history of the universe with unprecedented precision. One of the key techniques is the use of baryon acoustic oscillations, BAO. These are the fossilized imprints of the sound waves that propagated through the plasma of the early universe just before recombination. These sound waves left a characteristic scale, a preferred distance between galaxies, that can be measured today. By measuring this standard ruler at different points in cosmic history, astronomers can precisely track the expansion rate of the universe and therefore the influence of dark energy. Projects like the Dark Energy Survey, DES, and the upcoming Euclid mission and the Nancy Grace Roman Space Telescope are designed to map the positions of billions of galaxies and quasars across vast stretches of the universe. By combining BAO measurements with observations of Type 1a supernovae and gravitational lensing, these surveys aim to determine whether dark energy is truly the cosmological constant, a static property of space, or a dynamic, evolving field like quintessence. The answer to the dark energy mystery will determine the ultimate fate of the universe. If it is the cosmological constant, the Big Freeze is our destiny. If it is a dynamic field, the future could hold anything from a gentle fade to a violent Big Rip. The birth of galaxies was the beginning of our story. The nature of dark energy will write the final, epic conclusion. Let us conclude with a final reflection on the cosmic inventory we have assembled. 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. The fact that 95% of the universe is composed of things we cannot see, touch, or fully understand is a profound lesson in humility. It reminds us that our senses, our everyday experience, and even the standard model of particle physics only scratch the surface of reality. The universe is far stranger, far more mysterious, and far more vast than we can easily comprehend. The birth of galaxies, the creation of stars, the formation of planets, and the emergence of life, all of it is a tiny, beautiful accident, a fleeting moment of complexity built upon a foundation of invisible, unknown forces. The story of gravity and dark matter is the story of the universe's struggle to build structure against the relentless expansion of space. Our journey, from the quantum jitters of inflation to the accelerating expansion of the present day, is a testament to the power of human curiosity. We are the conscious product of this cosmic evolution, the mechanism by which the cosmos can reflect upon itself. The quest to understand the universe's origins is the quest to understand our place within it, and it is a journey that will continue for as long as we look up and wonder. We have focused on the galaxies, the bright islands of stars, but the vast majority of ordinary matter in the universe resides not within them, but in the space between them. The intergalactic medium, IgM. The IgM is the breath of the cosmos, the diffuse, tenuous gas that fills the voids and filaments of the cosmic web. The IgM is the reservoir of gas from which galaxies draw their fuel, and it is the medium through which the energy from supernovae and AGN feedback is transmitted. In the voids, the IgM is cold and mostly neutral, a relic of the cosmic dark ages. In the filaments, it is warmer, heated by the gravitational collapse of matter. And in the dense nodes of galaxy clusters, the IgM is a searing hot plasma, emitting X-rays, a direct consequence of the violent processes of galaxy formation and merging. The study of the IgM is crucial for understanding galaxy evolution. Galaxies are not closed systems. They are constantly exchanging matter and energy with the IgM. They accrete cold gas from the filaments to fuel star formation, and they expel hot, metal-enriched gas back into the IgM through galactic winds. This continuous cycle, the baryon cycle, is what regulates the growth of galaxies. Astronomers study the IgM by observing the light from distant quasars. As the quasar light travels across the universe, it passes through clouds of IgM gas, and the atoms in the gas absorb specific wavelengths of light, creating a series of absorption lines in the quasar's spectrum. This is known as the Lyman Alpha Forest, and it acts as a cosmic tomography, allowing us to map the density, temperature, and composition of the IgM across billions of light years. The IgM is the invisible, dynamic backdrop against which the drama of galaxy formation plays out. Our story has focused on the grand spirals and ellipticals, but the most numerous type of galaxy in the universe is the dwarf galaxy. These are small, faint, and often irregular galaxies, containing only a few million to a few billion stars. They are the building blocks of the cosmic web, the smallest clumps of matter that manage to form stars. The cold dark matter, CDM model of structure formation predicts that there should be a vast number of these small dark matter halos, and therefore a vast number of dwarf galaxies orbiting larger galaxies like the Milky Way. However, for decades, astronomers observed far fewer dwarf galaxies than the theory predicted. This was known as the missing satellites problem. The solution to this problem lies in the physics of star formation and feedback. The smallest dark matter halos are so shallow that the energy from just a few supernovae, or the intense UV radiation from the epoch of Rayonization, was enough to completely blow the gas out of the halo, preventing star formation. The dark matter halos are there, but they are dark galaxies, containing little to no visible stars. The discovery of ultra-faint dwarf galaxies in recent years, often through large-scale surveys, has helped to bridge the gap between theory and observation. These galaxies are incredibly dark, dominated by dark matter, with mass-to-light ratios that can exceed 1,000. They are the purest laboratories for studying dark matter, the ultimate proof that the invisible architect is real. The smallest galaxies are the most numerous, and they hold the key to understanding the full complexity of the hierarchical assembly process. The story of the early universe and the birth of galaxies is far from over. The next few decades promise a revolution in our understanding, driven by a new generation of colossal telescopes and ambitious space missions. On the ground, the extremely large telescope, ELT, in Chile, with its 39-meter mirror, will be the largest optical telescope in the world. It will allow astronomers to study the atmospheres of exoplanets, but more importantly for our story, it will be able to study the light from the very first galaxies in unprecedented detail, providing spectroscopic confirmation of the elements forged by the population 3 stars. In space, the Nancy Grace Roman Space Telescope will have a field of view 100 times larger than the Hubble Space Telescope, allowing it to map vast swathes of the sky and precisely measure the effects of dark energy and the distribution of dark matter through gravitational lensing. And finally, the Square Kilometre Array, SKA, a massive radio telescope array being built in South Africa and Australia, will be the ultimate tool for studying the epoch of Rayonization. It will be sensitive to the faint 21 centimeter signal from neutral hydrogen, allowing us to create a 3-dimensional map of the universe during the cosmic dark ages, and witness the battle for transparency as it unfolded. These instruments are the next chapters in our human story of cosmic discovery. They will allow us to push the boundaries of the observable universe, to refine our understanding of gravity and dark matter, and to continue the quest to understand how we came to be. The birth of galaxies was a monumental event, and the story of its discovery is a testament to the enduring power of human curiosity. To truly grasp the magnitude of this story, we must place the events on a clear, continuous timeline, a chronology of creation that stretches from the singularity to the present day. It begins at the Planck epoch, 10 to the power of negative 43 seconds after the start, where the laws of physics as we know them break down and all four fundamental forces are unified. Between 10 to the negative 35 and 10 to the negative 32 seconds during the inflationary epoch, the universe undergoes hyper-rapid exponential expansion, smoothing out the cosmos and stretching quantum fluctuations into the seeds of structure. By 10 to the negative 12 seconds, the electroweak epoch sees the electromagnetic and weak nuclear forces separate, leaving the universe as a hot, dense plasma. By the microsecond mark, or 10 to the negative 6 seconds, quarks combine to form protons and neutrons. 3 minutes into the life of the universe, Big Bang nucleosynthesis occurs. Protons and neutrons fuse to form the first light atomic nuclei, hydrogen, helium, and lithium, setting the elemental stage. It takes until 380,000 years for the universe to cool enough for electrons to combine with nuclei during the recombination era. Here, neutral atoms form and photons are released, creating the cosmic microwave background and plunging the cosmos into the dark ages. From 10 million to 400 million years, gravity, driven by dark matter, slowly gathers gas into mini-halos, though no stars or galaxies yet exist. This silence breaks at the 400 million year mark, known as the Cosmic Dawn, when the first population 3 stars ignite, ending the Dark Ages. This initiates the epoch of rionization, lasting up to the 1 billion year mark, where light from the first stars and quasars reionizes neutral hydrogen, making the universe transparent and allowing the first true proto-galaxies to form through hierarchical merging. By 3.8 billion years, we reach cosmic noon, the peak of star formation and black hole activity. Around 9.3 billion years, the expansion of the universe begins to accelerate, driven by the discovery of dark energy. This brings us to the present day, 13.8 billion years later. We exist in the stelliferous era, a time of mature galaxies, ongoing mergers, and the dominance of dark energy. Looking into the future, in about 4.5 billion years, the Milky Way and Andromeda galaxies will collide and merge to form a new, massive elliptical galaxy. Far beyond that, 10 to the power of 14 years from now, the stelliferous era will end as the last red dwarf stars burn out and the universe becomes dark. Finally, stretching from 10 to the power of 37 to 10 to the power of 100 years in the future, we enter the degenerate era. In this long, cold fade, the universe is filled with stellar remnants which slowly decay or are ejected from galaxies. This timeline is the backbone of our story, a reminder that the birth of galaxies was not a single event, but a long, complex process, a tale of gravity and dark matter unfolding over cosmic time. We have explored the how of galaxy formation, but the ultimate question remains: why? Why is there something rather than nothing? Why are the laws of physics so perfectly tuned to allow for the emergence of complexity, of stars, of galaxies, and of us? Science, by its nature, can only answer the how. It can describe the mechanism of inflation, the force of gravity, and the composition of dark matter. But the why remains in the realm of philosophy and metaphysics. The multiverse hypothesis attempts to sidestep the why by turning it into a statistical inevitability. If there are infinite universes, then our existence is simply a roll of the cosmic dice. But even this answer is unsatisfying to some. Perhaps the most profound answer lies in the very nature of the universe's evolution. The universe began in a state of maximum simplicity, a hot, uniform plasma. It has been on a relentless, irreversible journey toward complexity, a journey that has produced the intricate cosmic web, the dazzling spiral galaxies, and the conscious minds that can contemplate it all. The birth of galaxies is the most spectacular manifestation of this drive toward complexity. It is the moment when the smooth, featureless early universe gave way to the rich, structured, and beautiful cosmos we inhabit. It is a story that instills a sense of profound wonder, a reminder that we are not just observers, but participants in the greatest story ever told. The tale of gravity and dark matter is, ultimately, the tale of existence itself. Our story has taken us to the limits of time, but it is also constrained by the limits of space, the cosmic horizon. This is the boundary of the observable universe, the maximum distance from which light has had time to reach us since the Big Bang. Because the universe is 13.8 billion years old, one might assume the horizon is 13.8 billion light years away. But this ignores the expansion of space. The light we see today from the most distant galaxies has traveled for 13.8 billion years. But during that time, the space between us and the source has expanded. The actual distance to the cosmic horizon today is about 46.5 billion light years. The cosmic horizon is not a physical edge to the universe. It is a boundary of our knowledge, a limit imposed by the finite speed of light and the finite age of the cosmos. Everything we have discussed, inflation, the CMB, the birth of galaxies, took place within this observable bubble. But the universe itself is likely much, much larger, perhaps infinite. The existence of the cosmic horizon has profound implications for our story. It means that the universe we see is only a fraction of the whole. There are countless other galaxies, clusters, and superclusters beyond our horizon, forever hidden from our view. The birth of galaxies is an event that is happening everywhere, but we can only witness a small, albeit spectacular, part of the show. The cosmic horizon is a constant reminder of the vastness and the mystery that still lies beyond our grasp. Let us bring the focus back to our home, the Milky Way, and its ongoing evolution as a galactic ecosystem. Our galaxy is a dynamic, living entity, constantly recycling its matter and energy. The Milky Way is a spiral galaxy, characterized by a central bulge, a flat disk with spiral arms, and a vast, spherical halo of dark matter and old stars. The disk is the site of active star formation, fueled by the cold gas that is constantly being drawn in from the intergalactic medium. The spiral arms are density waves, regions where gas and stars are temporarily compressed, triggering the collapse of gas clouds and the birth of new stars. The central bulge is a dense, crowded region of old red stars surrounding the supermassive black hole, Sagittarius, A star. The halo is the ghostly graveyard of the dwarf galaxies that the Milky Way has consumed over billions of years. The Milky Way is a perfect example of the self-regulating system we discussed. The star formation in the disk is constantly being quenched by the feedback from supernovae. which stir up the gas and prevent it from collapsing. The central black hole, though currently quiet, has had periods of activity in the past, sending out powerful jets that have shaped the gas in the halo. The Milky Way is a mature galaxy, but it is still evolving, still accreting, still forming stars, and still on a collision course with Andromeda. It is a living testament to the power of gravity and dark matter, a beautiful, complex ecosystem that is the product of 13.8 billion years of cosmic evolution. We have reached the end of our epic journey, a journey that has taken us from the first fraction of a second after the Big Bang to the far, cold future of the universe. We have seen how the universe's greatest structures, the galaxies, were born from the smallest quantum jitters, guided by the invisible hand of dark matter and shaped by the relentless force of gravity. The story of the early universe and the birth of galaxies is the most profound narrative available to us. It is a story of creation, of destruction, of order, and of chaos. It is a story that is, in every sense, our own. We are the stardust, the conscious product of this cosmic evolution, the mechanism by which the universe can reflect upon its own origins. The quest to understand the universe's origins is the quest to understand our place within it. And it is a journey that will continue for as long as we look up and wonder. The night sky is not a static backdrop. It is a living, breathing history book, and every point of light is a word in the greatest story ever told. Let us close the loop on the cosmic microwave background, the universe's baby picture, and the blueprint for all structure. The discovery of the CMB in 1964 by Arno Penzias and Robert Wilson was one of the great accidental discoveries in science. They were testing a new, highly sensitive horn antenna for Bell Labs and kept finding a persistent, annoying hiss or noise that they could not eliminate. They tried everything, even cleaning out pigeon droppings from the antenna, but the noise persisted. Unbeknownst to them, a team of physicists at Princeton University, led by Robert Dicker, was preparing an experiment to search for this very radiation, which had been theoretically predicted decades earlier as a relic of the Big Bang. When Penzias and Wilson learned of the Princeton work, the pieces clicked into place. The noise was the faint uniform afterglow of the Big Bang itself. It was the universe's oldest light, a discovery that earned them the Nobel Prize and cemented the Big Bang as the leading cosmological model. The CMB is not just a historical artifact, it is a living laboratory. Future probes are focused on detecting the polarization of the CMB, which can reveal even more about the universe's infancy. Specifically, cosmologists are searching for B-mode polarization, a swirling pattern in the light that would be the direct signature of primordial gravitational waves, ripples in space-time generated during the inflationary epoch. The detection of B-modes would be the ultimate confirmation of inflation, providing a direct link between the quantum realm of the very early universe and the larger structures we see today. Experiments like BICEP and the South Pole Telescope are at the forefront of this search, peering into the deepest, coldest parts of the sky, hoping to find the faint swirling echo of the universe's first moments. The birth of galaxies was written in the temperature fluctuations of the CMB. The story of inflation is written in its polarization. The quest for this faint ancient signal is the final frontier in our tale of gravity and dark matter. Our understanding of the early universe and the birth of galaxies is a synthesis of observation and theory. We have the observational evidence from the CMB, the Hubble Space Telescope, and the James Webb Space Telescope, and we have the theoretical framework of general relativity and the cold dark matter model. But to bridge the gap between the smooth, early universe and the complex, clumpy cosmos we see today, we need a tool that can evolve the initial conditions forward in time: hydrodynamical simulations. These are not simple computer models. They are massive, complex computational experiments that attempt to recreate the entire history of the universe in a virtual box. They start with the initial conditions derived from the Planck satellite's CMB data, the tiny density fluctuations, and then let the forces of gravity, hydrodynamics, the flow of gas, and the physics of star formation and feedback take over. One of the most famous of these simulations is Illustris TNG, the next generation. Imagine a cube of the universe, hundreds of millions of light years on a side, containing billions of virtual particles representing dark matter, gas, stars, and black holes. The simulation tracks the gravitational interaction of the dark matter, the flow and cooling of the gas, the formation of stars when the gas reaches a critical density, the energy injection from supernova, stellar feedback, and the powerful jets and winds from supermassive black holes, AGN feedback. The success of Illustris TNG and similar simulations like EAGLE and Romulus is that they can reproduce the observed properties of the galaxy population with remarkable accuracy. They show how the dark matter web forms first, acting as the gravitational scaffolding. They show how the cold gas flows along the filaments and collects at the nodes, forming the first galaxies. Crucially, they show how the inclusion of feedback, the self-regulating processes driven by stars and black holes, is absolutely essential to prevent the formation of too many massive galaxies and to explain the observed diversity of galaxy types, from the star-forming spirals to the quiescent ellipticals. For example, the simulations can reproduce the bimodality of the galaxy population. The two distinct groups of red, dead, elliptical galaxies and blue, star-forming spiral galaxies. They show that the red galaxies are the result of major mergers and powerful AGN feedback that stripped them of their cold gas, while the blue galaxies have had a quieter, more continuous history of gas accretion. The simulations also provide a powerful tool for exploring the what-if scenarios. What if dark matter was warm instead of cold? What if the efficiency of stellar feedback was different? By tweaking the parameters of the simulation, cosmologists can test the robustness of the standard model and explore alternative theories. The universe in a box is a testament to the power of human intellect and technology. It is the ultimate bridge between the abstract equations of physics and the tangible reality of the night sky. It allows us to watch, in fast forward, the entire 13.8 billion year process of cosmic evolution, from the quantum jitters to the birth of galaxies. A process that is, at its heart, a tale of gravity and dark matter. The ability to hold the universe in a computer and watch it evolve is perhaps the most profound achievement in our quest to understand our cosmic origins. To truly appreciate the precision of the simulations, we must return to the Baryon acoustic oscillations, BAO. These are not just a tool for measuring dark energy. They are a fundamental feature of the cosmic web that the simulations must accurately reproduce. As we discussed, the BAO are the fossilized imprints of sound waves that traveled through the plasma of the early universe. When the universe became neutral at 380,000 years, these waves stopped, leaving a characteristic ripple in the distribution of matter. This ripple corresponds to a preferred distance, a standard ruler, of about 490 million light-years in the present-day universe. When astronomers map the distribution of galaxies in the cosmic web, they look for this subtle, statistical excess of galaxy pairs separated by this specific distance. The detection of the BAO peak in galaxy surveys is a monumental achievement, as it provides a direct, independent confirmation of the initial conditions set by the CMB and the subsequent evolution predicted by the lambda CDM model. The hydrodynamical simulations must be able to evolve the initial CMB fluctuations and maintain the integrity of this BAO signature as the universe forms stars, galaxies, and clusters. The fact that the simulations successfully reproduced the BAO scale in the final distribution of galaxies is a powerful validation of the underlying physics, particularly the interplay between dark matter and ordinary matter. The BAO is the ultimate cosmic yardstick, a precise measure of the universe's expansion history, and a crucial piece of evidence that links the smooth, early universe to the clumpy, structured cosmos we inhabit. It is a reminder that the birth of galaxies was not a random event, but a process governed by the precise, elegant physics of the Big Bang. And so, our journey concludes where it began, with a sense of profound wonder. We have traversed the vastness of cosmic time, from the fleeting moment of inflation to the distant, cold future. We have seen the universe's grandest structures, the galaxies, emerge from the smallest quantum fluctuations, guided by the invisible hand of dark matter and shaped by the relentless, all-encompassing force of gravity. The story of the early universe and the birth of galaxies is the most profound narrative available to us. It is a story of creation, of destruction, of order, and of chaos. It is a story that is, in every sense, our own. We are the stardust, the conscious product of this cosmic evolution, the mechanism by which the universe can reflect upon its own origins. The quest to understand the universe's origins is the quest to understand our place within it. And it is a journey that will continue for as long as we look up and wonder. The night sky is not a static backdrop. It is a living, breathing history book, and every point of light is a word in the greatest story ever told. Thank you for joining us on this deep dive into the cosmo depth. We hope this journey has ignited your curiosity and left you with a renewed appreciation for the incredible, complex, and beautiful universe we call home. Until next time, keep looking up